Haven't seen you in so long. Took your break. Okay, this week in lab, we'll finish experiment 20, so we're going to be doing part C, so make sure you remember your technician number so you know what enzyme you're using this week. You'll have your last quiz, and your experiment 17 report is due, so don't forget to have that ready to go in your notebooks, ready to hand in at the end of the lab period, so have it ready to go before you come to lab. Next week in lab, so we're going to have part of everybody's going to be checking out, but before that, in lab we have to have an experiment 20 discussion of the data from this week, so the whole lab will need to participate in that data discussion, and then evaluations will need to be filled out, and then the 1 credit students will be checking out. So it'll take an hour and a half, 2 hours or so to get through this. So plan on, even if you're taking the lab for 1 credit, you're still going to be in lab for, a couple hours next week. 2 credit people, we will do the in-lab discussion and evaluations, and then you'll be going to the library to start the independent project. Okay? Also next week on the syllabus, your experiment 20 report is due. Make sure to talk to or get the due date from your lab prof. They'll give you more specifics of when that actually is due. Okay. Midterm exam. So next week when we all gather together, we'll be gathering together for the exam, which will start right at 4 o'clock. There's a class in here until 3:50. So I'm going to have you guys wait out in the hallway until we get everything set for the exam, and then we'll have you guys come in when we've got all the exams ready and places for you all set to go. So when you come for the exam next week, wait until we have you come into the classroom, and then we'll get everything set so we can start right at 4 o'clock for the exam. And it's an hour exam, so you'll have from 4 till 5 to complete the exam. Make sure bring calculator with you with memory erase. Make sure bring ruler with you. Bring pencils and erasers with you for the exam. And then if you have academic support center paperwork that needs to be signed, I need to sign it ASAP for exams that need to go over there. Okay? So see me. Okay, so we're going to kind of review what experiment 20 we've done so far, which is kind of the abbreviated version. So at the beginning of experiment 20, the goal of the experiment was getting precursors to these compounds. So these were, based on the case study, these were the important compounds for what needed to, the pharmaceutical company needed to come up with. And so we needed precursors to that. And so the precursors to that were this guy as a methyl group, this guy as an ethyl group, this guy as a propyl group. Okay? And so this week, you've got your diester from a couple weeks ago. What you want to form is the precursors to these guys, depending on what your R group is on each of these. Okay? Now, had we done 20A, what we would have started with is 4-hydroxybenzoic acid. Okay, that would have been the starting material for 20A, and then we would have used Fischer Esterification to add on the first R group to make the first ester. Okay, but we didn't have 20A, so we started here with a methyl group here. So everybody has the methyl group on this side. All right. Then we went on and took that starting material into 20B and reacted it with an acid chloride impurity. And here is where we had variation amongst what people made depending on the R group here, depending on what acid chloride you used. And so then this week, we're going to take this guy and see, we're going to use pig liver esterase or orange peel esterase, depending on what your assignment is, and see if you get to the desired product that you want for the project. Okay? So before we really talk about today's experiment, we kind of need to get through a little bit of information about enzymes in general. So just some classifications of enzymes just out of McMurray itself. So I don't expect you to take in all of this table right at this moment. But different types of enzymes that can be used for different chemical transformations. We got transferases, hydrolysis, lysases, isomerases, ligases. So depending on the different type of chemical transformation we need to have happen, there's different enzymes that perform that job, okay? And they perform it in nature all the time. Now more and more people are starting to use them to do things synthetically, not just in nature. So we want to hydrolyze an ester. So we want either an esterase, or it's also known as a hydrolase, to hydrolyze the ester that we have. Hydrolyses are kind of the generic name for anything that's going to hydrolyze bond. The esterase is more specific to actually chewing on the actual ester compound. Okay, and so a little bit about how enzymes work. The enzymes and their substrates, the two of them coming together is a very specific situation to get things to work well. And sometimes some enzymes are so specific that you can get one enantiomer to work on an enzyme surface and be a good substrate for that enzyme, and another enantiomer won't work. So it can tell, enzymes can tell the difference between enantiomers in certain situations. And so there's a series of models that we consider when we're talking about enzymes, because not every enzyme works exactly the same way as another enzyme. And so the ones that we're going to talk about real briefly are the lock and key model, induced fit, and the binding pocket. And so a couple of these are up here. So the lock and key model is where you have very specific portion of the enzyme is fit just perfectly to fit the substrate that's going to come in there. And so if it's shaped any, like in this diagram, you've got this triangular portion here. If it's shaped any different than that, it's not going to be a good fit for the enzyme, and you're not going to get the enzyme and substrate to come together. And so this was kind of one of initial model really considered in enzymology, and it really helped explain the specificity of an enzyme. And it's still considered as a model of how enzymes work. Something else that kind of developed with more experiments is the induced fit model. So instead of it having to fit perfectly together like a lock and key, you can have an enzyme kind of shaped so that it can take on that substrate, and as they come together, they kind of mesh together to fit well together. So you can kind of think of that as like a baseball glove that will mesh around a baseball, but it's not exactly fit perfectly for that baseball until you squeeze it around the ball itself. Okay, so they come together and fit well together, but apart they don't necessarily look like they will completely fit together because they're not perfectly shaped like each other. So another model is then the binding pocket, and this is the model that they think describes what is going on with the pig liver esterase. And so this is, you've got a certain pocket that the substrate can bind in, and multiple different substrates can bind in that pocket, but it depends on how well they fit into that pocket. Okay, so it's built for certain substrates, and other ones can sometimes get in there, but if you change the substrate dramatically, it's not going to fit in that binding pocket. So you can have a little bit of variation, but you're probably not going to be able to accommodate huge variations. And so like I said, this is what is thought to be how the pig liver esterase works. And like this schematic is out of the paper that this whole experiment was based off of was this schematic of the binding pocket. And so there's a reason that we're looking at enzymatic esterification versus we could just go and use acid or base to catalyze the esterification and see what we get out. But the problem with that, if you look at both acid catalysis and base catalysis, is there isn't specificity towards what it's going to attack. So the next couple of mechanisms that I'm going over are in McMurray for the acid catalysis. So acid-catalyzed Ester hydrolysis. Is in McMurray. The 6th edition, it's on page 793. The 7th edition, it's on page 811. So if you haven't covered it yet, you will very soon look at acid-catalyzed ester hydrolysis. For the base-catalyzed ester hydrolysis, that for the 6th edition, it's like one page over, page 792. And for the 7th edition, it's page 810. So I'm going to kind of walk through that, those mechanisms right now and just give you a look at them and why they aren't necessarily specific for any certain substrate. They're going to attack all esters the same way. And so with the acid-catalyzed hydrolysis, we're going to use this acid to protonate the oxygen of our carbonyl, and so that allows water to come in and attack the carbon of the carbonyl. And so then we get this four-membered intermediate, our tetrahedral intermediate here, that then we've got a driving force here of we can lose either water, or we can, even better yet, we'll lose an alcohol if we collapse this intermediate. And so we've got a proton transfer that occurs with the water, or another proton out in your acid, because you are protonated, you're in acid here, to form our alcohol, and then we lose the proton off of our oxygen, get collapsed down of the carbonyl, and then we get our alcohol group to leave. And so in the end, what we're left with, we've got our alcohol. The other part of our ester is the carboxylic acid, and then because of acid catalysis, we've then got regeneration of H3O+, or regeneration of the acid. So with ester hydrolysis, you will always create a carboxylic acid and the corresponding alcohol. Okay, so in what you guys are looking at with your compound, you're going to have a carboxylic acid, maybe not necessarily attached to your compound, and a corresponding alcohol that's going to be formed. But this whole reaction isn't specific for any type of ester. It will work with some a little bit better than others, but it's not going to pick one side of a diester over another side. It would attack both sides. Okay. So same with base catalysis. And so now we're in base, so we're not protonating our carbonyl. Instead, our OH from our base is going to directly attack our carbonyl. Then we have collapse of that carbonyl and we lose OR minus. But then we can take a proton from the carboxylic acid that forms from our OH here. And so here we've got our alcohol, and then with base catalysis, you just have to do acid workup to then get the final unprotonated or neutral, not ionic, carboxylic acid. So it is protonated. So again, we've got our carboxylic acid here, and we've got our alcohol that is formed from the hydrolysis. And again, with the base, still is not going to be specific to either side of your diester. It would attack both sides easily, okay? So that's why we want to look at enzymatic catalysis, because then we've got more specificity with what's going on. So in your lab manual, it shows you a kind of a schematic of the binding pocket of pig liver esterase. And so what is considered to be the common scheme for the pig liver esterase, or the common model for the catalytic system, is called the serine hydrolase triad. And the reason for the triad, oops, sorry, catalytic part here, catalytic triad, most important. And so the triad part comes from, there's actually 3 amino acid residues that are involved in this. So you've got definitely your serine, you've got histidine, and then you've got aspartic acid or aspartate, depending on what form it's in, whether it's protonated or not. So SCR is how you represent the serine, HIS, histidine, ASP is the aspartic acid or aspartate. So these 3 residues have been found to be important in the binding pocket of that enzyme, okay? Now it's not like you can just assemble these 3 residues and you will get ester hydrolysis, but they, in amongst the rest of the binding pocket, which is also important, these play an active role in the actual hydrolysis reaction. And so what happens, so we've got our aspartate here, and the catalytic cycle, the triad, is we have our aspartate, it deprotonates the neighboring NH off of the histidine, which then causes flow of electrons to then deprotonate the OH off the serine to then cause attack of our ester. And so then when you're done with this part of the cycle, so we've gone through all of these steps, in the end we have lost our alcohol out of this whole sequence of events, okay? So if we attack the carbonyl and it goes up and comes back down, we lose our OR prime, protonate it, we get our alcohol, and then we've got all aspartic acid, our histidine, and our serine again, okay? But we need to return our enzyme back to where it was previously, okay? So this is kind of like the forward direction. We've got to go backwards, and we already have our alcohol that we said we were going to get with the hydrolysis. So now, we are going to go backwards again, okay? So we've got now water involved because we're in an enzyme. We've got lots of water around. It'll attack this carbonyl here off the serine. We've got our electron flow to the oxygen and then back down, and then we lose this bond here to the proton. Electron flow this direction from the histidine, then takes this proton back to the aspartate. So then what we recover from all this is back to aspartate, back to the original histidine, back to the original serine, and now we have our carboxylic acid. Okay, so the forward direction gave us the alcohol, the backwards direction has given us our carboxylic acid. And so now, and we've returned the triad back to where it started, okay? And so with it being an enzyme that is going to act as a catalyst, and that's the definition of the enzymes, they catalyze these reactions, we need to return it back to where it started, okay? And so, in all this, something that we need to consider is that whole forward and backwards reaction where we had the enzyme and the substrate come together and then we returned our enzyme back to its original state is considered one turnover. So where we've got the enzyme and the substrate, they come together as the enzyme and the substrate and then come apart again as the original enzyme, and then the product or products is considered one turnover when you're talking about enzymology. Okay? And so that's going to be the turnover or the efficiency is something that you're going to want to consider. So how many reactions can you get out of the enzyme? And so we're going to measure that by how complete our reactions go. But the more reactions you can get out of one enzyme, the more efficient that enzyme is. So the greater the number of turnovers you get out of an enzyme, the better that enzyme is at doing its job. Okay? And so we're going to look at that in terms of what products we get out for experiment 20. So we want to remember, this is where we're starting. We're starting with our diester, okay? And so this guy here is our desired product, okay? So there's, out of this experiment this week, there's 4 possible things that could come out of it, okay? So we could come out of it with our 20B product, like, so nothing happens, which that is a possibility. It doesn't change our 20B product, okay? So the product you get out is the same thing you put in, your experiment 20B product. Now, not what you want, but it is still a possibility for what could happen this week. Or you could get the desired product, so that would have been the 20A product had we made it, or our methyl 4-hydroxybenzoate that we started with at the start of a couple of weeks ago. So this is our desired product. Something else that is a possibility is actually eating the other side, the other ester. Okay, so we want to chew off this ester. It is possible you could chew off the other ester. And so if you do that, you'll have the ester that you made 2 weeks ago intact, but we'll have the carboxylic acid over here. Okay? So if you think about the hydrolysis here, here you're going to lose the alcohol off this side and have the carboxylic acid. Here you're forming the alcohol, and what else is formed is then the carboxylic acid. So remember, you've always got both of them, alcohol and carboxylic acid, if you get hydrolysis. Or the other possibility is you get both sides chewed off. And so that would have, had we done 20A, you get back what you would have started with 20A. But since we didn't get that, if you get both sides chewed off, it's the 4-hydroxybenzoic acid is what you're going to get back. Okay? And so starting material is meaning, had we done 20A, that would have been the starting material. Okay? So does everybody see where these 4 possibilities come from? Okay. So keep that in mind when you're evaluating what's going on with your reaction. There's 4 things that can come out of it. Okay? And so what you are going to do is assess your own experiment, and we'll end up filling up this table here with what happens in your experiment. Okay? And so max time for this table is how long did you stir it. Okay? So you're going to stir up to 3 hours. We'll talk about that here in a minute. We're not going to calculate a yield for this reaction because it's really hard to do that. We're going to calculate a mass recovery, so a lot like we did with experiment 7. So you'll take what you're starting with, the mass you're starting with, and take the mass you ended with, and so take final mass over starting mass times 100%, that's your mass recovery. Okay, does everybody understand that? Then this is our percentage of what we get as far as products. So starting material is pointing at, do we get 4-hydroxybenzoic acid? Percent A means percent of the methyl 4-hydroxybenzoate that you started with 2 weeks ago. Okay, so this is A, but everybody is going to have the methyl group here. B is your product from 2 weeks ago, and D is chewing off not the ester you made last week, but chewing off the methyl benzoate that you started with. Okay? So does everybody understand the pieces to this table? Because in some form, your lab prof's going to have you fill out information for this table. Okay? Whether they do a Google Doc or just send you the table and you send back your entry for the table, somehow you're going to be filling out this table. Okay? So, as far as time for the reaction, it's going to stir for up to 3 hours, okay? But what we're going to do is we're going to monitor this reaction by TLC, okay? So we're going to TLC your reaction at 0 hours, so right when you mix everything together, okay? Everybody will TLC at that point. You'll TLC at 1.5 hours to see where things are at. And then if it's still not done in 1.5 hours, then you'll TLC in 3 hours, or maybe it's kind of close here, so you'll adjust this 3 hours accordingly, okay? The standards that you're going to use, so you've got your methyl 4-hydroxybenzoate. So we've still got this standard from a couple weeks ago. And you also have your 20B product, okay? So you're going to, on a TLC plate, you're going to be spotting 3 different things, okay? The methyl 4-hydroxybenzoate, your 20B product, so you need to set aside, don't use all of your 20B product for experiment 20C. Make sure you set a little bit aside for a TLC standard, okay? In your lab manual on page, I think it's 20-8 tells you what to do. You put that together, okay? You're going to dissolve a little bit in ether. And then you'll have your reaction mixture. Now the thing is these enzymes are in water. So we're using this mixture of, we've got some acetone, and then the enzymes themselves are made up in an aqueous buffer, okay? So when you're spotting a TLC plate, you're going to be spotting with something aqueous. So you've got to spot the TLC plate and then dry it, and then spot it again. Otherwise, if you keep spotting in the same spot and it doesn't dry, you're going to chew up that silica, okay? So you've got to be a little bit more careful this week than you have been with your spotting, because when you're spotting that reaction mixture, you've got to make sure it dries in between spots and make sure that it's completely dry before you develop it, okay? So be careful spotting the aqueous mixtures. Okay, and then once you have determined that your reaction is done, or we've gotten to 3 hours of stirring, you're going to be done with your reaction. Okay. Now for the 2 different enzymes, we've got the pig liver esterase. You can use up to 0.2 grams of your 20B product. Okay, so if you have pig liver esterase, you're going to use up to 20.2 grams. Okay, otherwise you'll get too much because you need 45 mils per 0.1 grams. So if you use any more than that, you won't be able to fit it all in your separatory funnel when you go to work it up. Orange peel esterase you can use up to 0.3 grams, okay? And so you'll scale up if you use more than the ratio of enzyme to your 20B product. So if you use 0.2 grams of 20B product with pig liver esterase, it says 45 mils of esterase per 0.1 gram. So if you use 0.2, you're going to use 90 mils. With the orange peel esterase, if you use up to 0.3 grams, it's 10 mils per 0.1 gram, so you use 30 mils of the orange peel esterase mixture, okay? What you're also going to need to do is probably scale up the amount of acetone that you use to get everything dissolved if you scale these up. So scale up the acetone according to how you scaled up your product from what is written in your lab manual, okay? But don't use more than this for either the enzymes, all right? When you're done with the reaction, you're going to add some ether to the reaction, and then you're just going to separate the two layers, and then you need to dry with magnesium sulfate. Orange peel esterase gets a bit of an emulsion during the workup. So you'll probably have to use the saturated sodium chloride solution to help break up that emulsion, okay? And you may even need to kind of use magnesium sulfate to kind of break it up too, okay? So the orange peel esterase people, if you're having trouble with emulsions, make sure to talk to your lab prof. You're probably going to need to wash with sodium chloride solution to help break up that emulsion, okay? The other thing with orange peel esterase people, and even pig liver esterase, when you're shaking your sep funnel, you know, cap it, invert it, move it back and forth, get the layers mixed, but don't shake it really hard. That'll help prevent huge emulsions from forming, okay? Shake it so that the layers are mixed, but don't shake the heck out of it, and it'll help with the emulsion problem, okay? So then, data you need to collect. So you're going to, once you're done, you dry with magnesium sulfate, you're going to filter, you're going to rotovap, you're going to put on the high vacuum pump, so similar to what we did a couple weeks ago. You'll need your yield, you'll need to make an NMR sample, you'll need IR if you have enough material for it, you'll need melting point maybe if you have a solid, okay? So this is the data you'll need to collect. This one's kind of really an iffy here. Remember, the yield is just a mass recovery, okay? So it's not a regular percent yield. You're just going to figure out your percent mass recovery. NMR sample you'll prepare just like you have before, but be careful. Make sure no water is present in your NMR sample. So especially the orange peel esterase people, make sure you don't have any water in your NMR sample, or you'll have to re-prepare it, okay? And then you'll make your IR sample. For the IRs, make sure you use the IR closest to the hallway in 3123. Don't use it closest to the lab, because PChem's using the IR closest to the lab. Yes, Gavin?
What method are we supposed to use to tell our different possible products apart?
Well, you've got your standards, right? Mm-hmm. So you've got what basically was 28. You've got 20B. You don't have a standard for 4-hydroxy benzoic acid, but you could approximate what type of RF value it would have. And you've got D, so you could kind of approximate where those RF values would fall, okay? So you've already got a couple things to figure it out, okay? The other thing you're going to use is NMR. So what I'm going to do is I'm going to post on Moodle. You're going to need the NMR for your 4-hydroxy, or for your methyl 4-hydroxybenzoate, okay? So I'm going to post the NMR for this guy. I'll run it when I run my lab sections NMRs tomorrow, okay? So you need this for comparison for your NMR data. You also have your 20B NMR. You'll be getting that back, okay? in the NMR data, your aromatic protons should resolve from each other, okay? So you should see a difference of aromatic protons with this guy versus your 20B product, okay? And so, versus the other possibilities. So you're going to use those aromatic protons to figure out your percentage of what product is present, okay? So you're using your aromatic protons basically for filling out that table, okay? And remember with NMR, you're talking about, NMR is always talking about moles, not grams. You're looking at relative moles of protons, not explicit grams, okay? So keep that in mind, okay? But use your aromatic protons and use the data that you have, what's posted on Moodle, your experiment 20, be NMR to try and figure out what's going on in your NMR itself, okay? And so then your percentages for percent starting material, percentage A, percentage B, percentage D, whatever it is going to come from the relative percentages from your aromatic protons. So if you get 100% conversion, it's going to be 100% whatever. Or if you don't get any reaction, it's still 100% B, okay? If you get partial reaction, then it's going to be partial B and partial something else, okay? So you have to figure out what that is, all right? But you will have the data that you need to do that, okay? All right, everyone's set with this part here? Okay, so now what I'm going to do is I need to quickly, in 12 minutes, go through the practice midterm exam. Move this guy over. I'm going to move it here so it's a little bit easier to see bigger pages. All right, so here we go. See how fast we can do this. Okay, so the first question was, which pair of starting materials along with the appropriate base and solvent could be used to make cis and trans mixture of the methyl cinnamate that was the product that we're talking about for this series of questions. And so we've got A, benzaldehyde, and our salt basically from experiment experiment 17. Or we make the triphenylphosphine salt, and then we've got this illite here, or esteraldehyde here, or we've got either pair, A or B, or neither pair. And so what the answer ends up being, if you look at the Wittig reaction of this pair or this pair, either one of them will work. Either one of them will get you to that product that you wanted, okay? So the answer is C on that one. Which of the following ways will it be possible to tell apart the HA and HB trans protons? We're talking about still the methyl cinnamate. They will have different multiplicity splitting patterns. Will they have different splitting patterns? No. They will have different coupling constants. Yes. Yes. They will have different chemical shifts. Yes. Possibly. All of the above, or both A and B, but not C. And actually, sorry, back to the, they will differ in coupling constants. There won't really be any difference in coupling constants, right? Because there's nothing else coupling with A or B. So it's not like experiment 17 that they differ because then of the secondary splitting. There is no secondary splitting. So if you've got cis A and B, they're both going to have the same coupling constant. If you have trans A and B, they're both going to have the same coupling constant. So the answer for that one is C. They will differ by chemical shift. How many non-equivalent protons are there in trans-methyl cinnamate? Q's on that one? 1, 2. So we don't have proton here, so 1, 2, 3, right? So you have 3 inequivalent aromatic protons. What would happen in your column chromatography separation if instead of using 4:1 hexane ethyl acetate, you use 40:1 hexane ethyl acetate? There would be no change. No. The more polar compounds would elute first. No, because you've made everything a lot less polar. The less polar compounds would elute first, but before they eluted last. No. Now all the compounds would elute much sooner. No, right? Now all the compounds would elute much later, but in the same order as before. So the answer is E. Okay. So here we are back with our methyl cinnamate again. So we've got this whole scenario of what happened. 2 students are working through their TLC data, and we've got this TLC information here based on what happened with their reactions. And so student 2 combined and wrote evap fractions 2 through 4. Student 1 only evaporated fraction 2. Okay? So we're basically going to be referring to here and the difference between student 1 and student 2. So what will student 2 see in the NMR? Student 2 combined and wrote evap fractions 2 through 4. So we've got 2, 3, and 4. So we've got a lot of things in 2, 3, and 4. You'll probably see both the cis and the trans. Starting methyl cinnamate, probably more trans than cis, and you will see starting material. Okay. Which student had the most material to go on to the next step with? That's going to be student 2 because they combined student fractions 2 through 4. Okay. Which student had the purest material? That's going to be student 1 because they only used the fraction with just product in it. Which student will have the higher percent yield if both students probably subtracted out impurities based on NMR results? That would be student 2 because you still ended up combining more product than student 1 did with just fraction 2. Which student's result more accurately indicates the true cis-trans selectivity of the Wittig reaction? It's going to be student 2's. And then what is the probable identity of the low RF value streaky spot in fraction 10? So this guy here, it could possibly be cinnamic acid or triphenylphosphine oxide. Which is more polar, the trans-methyl cinnamate or the cis-methyl cinnamate? And that comes from description here of what they collected. Student 1 only had fraction 2, and it was mostly trans-methyl cinnamate. So the top spot was mostly trans. The bottom spot of the product was mostly cis, and that's the more polar spot. So it's the cis product. Okay, question 6, like the whole series has to do with the Fischer Esterification, so I'm going to kind of go through it even super fast, but it's important for you to still be able to understand this because you're going to cover Fischer Esterification in lecture. So since we didn't do that reaction, we're not going to specifically ask you questions about the Fischer Esterification, but it's still important to understand. So the first question is, we've got this Fischer Esterification. Which of these mechanistic steps did not occur? And so with the Fischer esterification, everything doesn't happen just in one step here, so D is the answer. So just make sure for lecture you understand why these are all true possibilities, okay? In this reaction, the equilibrium is driven to the right. What we would have done in 20A is use a lot of alcohol to push it to the right. So it's an equilibrium reaction. We'd use a lot of alcohol, so in this case we would have used a lot of methanol to do that. Now this one is something, whether we did the Fischer esterification or not, you should be able to use TLC to evaluate what's going on, okay? So we've got these set of TLC plates. We went from benzoic acid to methylbenzoate. Column A represents the reaction at time 0. Column B represents the reaction halfway through the reflux. And so what we're looking for is that partially, what would represent that partially completed reaction. So A isn't we don't see any partial reaction. We've got starting material and we've got product. B, we've got starting material and product, although probably different RF values than we would have had for benzoic acid and then a benzoate. C, we've got starting material, and then halfway through we do see starting material and product, so that's probably the best representation, because D shows the same idea, but again, the benzoic acid is going to be more polar than the benzoate, so your starting material is going to be more polar than your product. Part D is basically yield calculation. You're starting with 3.62 grams benzoic acid. You have excess sulfuric acid and methanol. You need to figure out what is the theoretical yield. So you just have to go through the calculation, figure out your moles of benzoic acid, then figure out moles of benzoate, and figure out the theoretical yield, and then go through and use your theoretical yield to figure out your percent yield. Okay? So straightforward yield calculation. Okay, got unknowns here. We got to figure out, okay, so some student lost their backpack at Phillips, and they had no idea what they had used for experiment 20B, but they had NMR data to look at it, okay? And so we've got this NMR spectrum of the 20B product, and so you guys, knowing that you started with methyl 4-hydroxybenzoate, know that the methyl group for that starting material is farther this way. So this isn't going to be methyl group on that side of the compound, okay, for 20B. And so then we've got aromatic protons, and we've got what looks like an ethyl group. We've got a triplet and a doublet, and the integration corresponds. So this would be the product that we would get, where the methyl group is over here on this ester, not the benzoate ester. The ethyl group is on the benzoate ester. Okay. 20B, we've got, why did we use our our washes for 20B? The HCl wash is to get rid of the pyridine. It protonates the pyridine, and then it goes into the aqueous layer, and you can remove it. So you could either explain that or show it as a reaction that you react pyridine with HCl. This is the salt you get. That's going to go into the aqueous layer. NaOH wash was used to get rid of remaining 28 product or remaining methyl 4-hydroxybenzoate in your case. And so it deprotonates at the phenol, and so then you get the sodium salt. That's going to go into the aqueous layer and remove it from the organic layer. So either in words or showing the reaction would be sufficient answer. Okay. Question 9, this is just a percent recovery question from experiment 20C, okay? You start with 0.27 grams of your 20B product. The student used pig liver esterase. When they were done, they got 0.14 grams of part C product. What's their mass recovery? 0.14 grams, so that's their 20C product, divided by the 0.27 grams that they started with, times 100%, that's their mass recovery. Okay, so good example for this week for what you will need to do. Is the 2,4-DMP test sufficient to differentiate between the following structures? So we've got an ester, we've got an aldehyde. Yes, 2,4-DMP is not going to react with the ester, but it will react with the aldehyde. So you could use that as a characterization test between these two compounds. Okay, and you'll get a yellow precipitate with the aldehyde. Okay, we've got this unknown here. We've got the formula C5H5NO. It has a positive sodium fusion test, positive ferric chloride test. What does that tell you about ferric chloride? So it's a phenol, but we've only got C5, right? So that probably means the nitrogen somehow is a part of the ring. Show your work for the structure. We've also got here, in the aromatic region, we've got doublet, two protons, doublet worth 2 protons, so we've got para substitution, and we have one broad singlet, which probably points to the OH, right? So it's para substituted ring, we need a phenol, and so this, you'd have the phenolic pyridine is what you would have as far as the product. last page for lightning speed review here. A compound with the following IR spectrum is most likely to give a positive result for which characterization test? We've got DNP, we've got bromine, we've got ferric ammonium nitrate, we've got the sodium fusion test. So from this IR, what stands out as you is going to be an answer for this guy? Ferric ammonium nitrate, right? Huge OH stretch. Ferric ammonium nitrate is going to give you a positive test. Okay, so then for this final question, we've got an unknown. It gives a reddish purple color when treated with hydroxylamine and 5% ferric acid. So the hydroxamate tests for what compounds? Esters. The proton NMR was also obtained. Get the information of the structure which is most consistent. Okay, so first of all, we've got to look for an ester. So what has an ester with it? It's going to be B, right? It has the ester. So we've got aromatic protons. Okay, we've got a singlet. That would correspond to that methyl group. And we've got two triplets, which would correspond to these two methylenes. So that would correspond to the answer is B. Okay? And I did it with only 1 extra minute. So remember, next week, be here at 4 o'clock on time. We'll start the exam. Make sure rulers, calculators with memory erased pencils with you. You'll have an hour to complete the exam.